What do we mean by power in terms of physics? Power is the rate at which work is done, or more generally, power is the rate of energy transfer by any method. And what do I mean by any method? Well, we could transfer energy through thermal conduction, for example, where heat energy is being transferred from a hotter object to a colder one. Or we could consider the conversion of electrical energy into electromagnetic energy in a light bulb. So a 100-watt light bulb will convert 100 joules of electrical energy into electromagnetic energy, mostly in the form of heat and light, every single second. So that would be 100 joules per second. But let's break down the concept of power a bit further. If the work done on an object has some value in joules, which we'll call W, so this is the work done. And remember from a previous lesson, we learned that work is defined as the energy transferred to or from an object via the application of a force along a displacement. For example, if we have a block here, and we apply a force to this block that causes the block to move a distance of d, then the work done on this block is equal to the force multiplied by the distance. Now, if this constant force here isn't in the same direction as the displacement, say if the force was at an angle to the displacement of alpha, then we'd need to add in a cosine alpha to this formula here. So if the work done on this object is W, and this occurs over some time interval delta t, then the average power delivered to this object here over this time interval is equal to the work done on this object divided by the time interval. And this has units of watts or joules per second. In other words, power is the amount of work done or energy transferred per unit time. But when our force here acts in the same direction as the object's motion, as we looked at previously, then our power equation can be simplified to this. Power is equal to force multiplied by the distance the object moves divided by the time it takes for the object to move that distance. So what you'll notice here is that this distance over time section of the formula is simply the speed of this object. Distance over time is equal to the velocity. So we can further rewrite this equation, this power equation, as power is equal to the force applied to the object multiplied by its velocity. Okay, let's do some example problems that will help us understand this concept of power even further. So problem 1 says a 76 kilogram block is being raised by 1 meter over a time period of 1 second, as shown in setup on the left here. If the block is moving at a constant velocity and there is no friction in the pulley here, how much power does this horse need to produce to complete this task? So let's first write out our equation for power. So as we stated a few moments ago, power is equal to the work done divided by the time over which that work is done. And because our force here is acting in the same direction as the motion of the block, we can simplify work to force multiplied by distance over delta t. So power is the rate at which work is done. Our horse is doing work on this box by providing an upward tension force on this rope. But because the box has a mass and is within a gravitational field, the box also has a force pulling it downward. And this force is the weight of the box. So let's draw a free body diagram to show you exactly what's going on here. So the body we're interested in is our box. Our box is attached to a rope that's being pulled upward with a force of T. This is our tension. But the box also has a weight. It has a mass of 76 kilograms and it's within a gravitational field, which means it's got a force of gravity pulling it downward, which equals its mass times the acceleration due to gravity. Now our question says that the block is moving at a constant velocity. Now why is this important here? If this block's velocity doesn't change over this 1 second period here, then the acceleration is zero. Remember, the acceleration of an object is equal to its change in velocity over its change in time, which equals its final velocity minus its initial velocity divided by the time between these two velocities. So if the velocity doesn't change, then the final velocity and the initial velocity are exactly the same, and this term here will equal zero. So the acceleration will be zero. So when the acceleration is zero, this also means, according to Newton's second law, that the net force on this box is going to equal zero. So if the net force on this block is zero, that must mean the magnitude of the tension pulling upwards is going to equal the weight of the box. So tension minus mg is going to equal zero, because these magnitudes are the same. This means that the tension is equal to the weight of the box during this 1 second time period. We know our force term here, the tension pulling up the box, is equal to the weight of the box, mass times gravitational acceleration. So mg multiplied by the distance over the time period. So we have the mass of the block, 76 kilograms, 76.0 kilograms, multiplied by the acceleration due to gravity, 9.81 meters per second squared, multiplied by the distance the block is moving, 1.00 meters, divided by the 1 second time period, 1.00 seconds. And when we sum this all together, we get a power of 746 watts to 3 significant figures. And this is actually equal to 1 horsepower. So 1 horsepower is equal to 746 watts. So our second problem states we have a 1,000 kilogram car that's accelerating uniformly from rest to 27 meters per second in 5 seconds. Part A says, what's the work done on the car during this time interval? So we learned in a previous lesson on the work kinetic energy theorem that the net work done on an object is equal to the difference in the object's final and initial kinetic energy. In our question, work is being done on our car, causing it to increase its speed, and therefore its kinetic energy. So the net work done on this car is equal to the change in its kinetic energy, which equals the final kinetic energy of the car minus its initial kinetic energy. And remember, kinetic energy is equal to half times the mass of the object times its velocity squared. And we can factor this equation. We can factor out the half term here and the mass to give us this equation here. So from this, we can work out the net work done on this car as it goes from rest, 0 meters per second, up to 27 meters per second. So we know the mass of the car. That's 1,000 kilograms, multiplied by its final velocity squared, 27.0 meters per second squared, minus 0 meters per second squared. And this gives us a final value of 3.65 times 10 to the 5 joules. To 3 significant figures. But we've performed this amount of work over a 5-second time period. And that's what we're going to do in part B. We're going to find out the power delivered by the engine over 5 seconds. So how can we do this? Well, the power is simply our work done on our car divided by this time interval. So to get our car moving from 0 to 27 meters per second, which is roughly 60 miles per hour in 5 seconds, requires this amount of power from the engine. So power is equal to the net work done on the car, 3.65 times 10 to the 5 joules, divided by this 5 seconds. And that is equal to 7.29 times 10 to the 4 watts, to 3 significant figures, or 72.9 kilowatts of power.